Hi! Today's lesson is about the organization of the periodic table. For homework, you were asked to write the exponential notation for the valence shell electrons of the first 20 elements on our periodic table. And you had to write every element's data in their respective boxes. And this is what your homework should look like in terms of checking answers. Let's work through organizing the next 10 electrons. Here we are at element number 21. We know that that 21st electron is going to go into the 3d orbital. The way I'd like for us to write it is to recognize that 4s2 technically is our valence shell. It's our highest or outermost energy level. However, that 21st electron is going into the 3d1 spot. The 22nd electron will go into 3d2. But 4s2 is our valence shell, so I'd like to write it. The 23rd electron goes into the 3d3, but 4s2 really is the valence shell. The electrons in the 3d3 have more energy, but remember that they're in the third principal energy level. So it's not going to be our valence shell, despite the fact that they have more energy. My 24th electron, that of chromium, we want to write 4s2, 3d4. But that's not what nature does. Remember that nature takes one electron from the s to make it half filled and puts it into the d to make that half filled as well. That half filled s, half filled d sublevel combination is a more stable arrangement than the 4s2 3d4. Our 25th electron will go into the 3d5. However, the 4s2 is technically our valence shell. 26th electron, I'm sure you can get the hang of the pattern here. 27th. 28th. The 29th electron in copper, we want to write 4s2, 3d9, because that's the pattern that we're following, but we have to remember that that's not what nature likes. In this instance, nature wants to take one electron from the s to make it half filled and put it into the d so that the d is fully filled. That combination of half-filled S, fully filled D, is more stable to nature than the pattern you would expect. Our 30th electron goes into that 3d10 spot. And now what about our 31st electron? What will the valence shell electron configuration notation look like? It'll look like 4s2, 4p1. Let's finish out this row. Let's organize the 37th electron. If you think back to our diagonal rule, if you need to go back to the notes from the prior lesson, you're more than welcome to do so. But if I've got one more electron, 37 electrons that I need to organize, where's that 37th electron going to go? Well, my element, whose atomic number is 37, is going to be located here. And my valence shell will be 5s1. the 38th electron, the valence shell notation will be 5s2. And let's go one more. What do you suppose that next electron will look like, or where it will go? It's going to go into the 4d1 spot. But remember, that's not technically the valence shell. The valence shell is your highest or outermost energy level. And in this case, that would be energy level 5. So let's pause for a second and look to see if we can come up with some other patterns. I'm sure you're able to look going downwards. For example, we could predict correctly that the information in this next box will say 6s1, and information in the box below that will say 7s1. If I come to the box to the right of 6s1, I'm able to predict correctly that it will say 6s2. And the one beneath that will say 7s2. What we've just done is found the pattern for what's referred to as the S block elements. And we can't forget about helium. So this green for me highlighting, those are collectively referred to as the S block elements. In other words, their valence shell electrons are filling the S sublevel. Why is helium positioned all the way over here to the right? Why isn't it positioned directly to hydrogen's right, above that of beryllium? We'll get to that in just a minute, but you will find some periodic tables that actually put helium in both locations. You'll see it appear twice. But there is a reason why helium is positioned over here to the right, and we'll get to that momentarily. Let's look for some more patterns. I'm sure over here on the right-hand side of the periodic table, you're able to start to make predictions here too. You know that this next box will say 5s2, 5p1. And you know that the next box will say 5s2, 5p2. And the box after that will say 5s2, 5p3. And so on and so on and so on until we get to 5s2, 5p6. And I bet you're able to predict that the box beneath that will say 6s2, 6p6. And the box beneath that will say 7s2, 7p6. This section on the right-hand side of the periodic table that follows the pattern of filling the P sublevel is referred to as the P block elements. In other words, the valence electrons for these elements are filling or occupying the P sublevel. The maximum number of electrons that can go into the P sublevel are 6, and you'll notice that these elements are grouped in groups of 6. Another observation for patterns that you hopefully are picking up on is the numbering system. The S and P blocks, their numbers match those of the periodic table rows. In other words, row number 1 is energy level 1. Row number 2 is energy level number 2, and so on down the list. When we first learned about the quantum mechanical model of the atom, we learned that there are a maximum of 7 principal energy levels. And wouldn't you know it, there are 7 rows on the periodic table. The rows are called periods. Periods are what goes left to right, side to side on the periodic table. The period number is equal to the principal energy level or rings, around the nucleus for your S and your P block elements. Some other patterns. You're probably able to predict that if I move through these next 9 boxes, the boxes will say 5s2, 4d2, 5s2, 4d3, 5s1, 4d5. Remember, that's our exception, half filled S, half filled D. 5s2, 4d5, and so on. I'll just skip ahead. This one will say 5s1. Oh, excuse me, I'm in the wrong box. I want it to be in Silver's box. 5s1, 4d10, and moving over 1, 5s2, 4d10. If I were coming down here into period 6, I would predict that this would say 6s2, 5d1. And I'll stop here for a moment, with our patterns, that is, and talk about what this center section here is called. I'm highlighting it in yellow. This section here in the middle of our periodic table, again highlighted in yellow. Oh, I'm not so sure how great this yellow color is going to be. Sorry. They are the D block elements. Let me go over that again, perhaps in a darker color. D block elements. And again, that's our yellow highlighted section here in the middle. If you remember when we were writing electron configurations, after the D sublevel, we would always write a total of 5 orbitals. If each of these orbitals can hold 2 electrons, the maximum number of electrons that D can hold is 10. And when you count the number of elements that are in these blocks, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this grouping of the 10 elements is meant to be the electrons going into the D sublevel. And that brings us to the last sublevel that we had, the F, or the flower. I hope that you're recalling, after we would write F, there would be 7 dashes. In other words, F could hold a maximum of 14 electrons. If you count very carefully on this one, here are the 14 electrons that would fill the F sublevel. We'll enter the data in just a moment. My pink highlighting This is the F block elements. When you look at our highlighting, you'll notice that we, quote, skipped a box. The skipping box is this here. The 6s2 5d1 is the same element here. 6s2 5d1. Our first element in the F block, it's going to go into 4f1. But that electron doesn't get there until 1 went into 5d and until that S block in energy level 6 got filled. The next box over would be the second electron in the 4f sublevel, but that doesn't get placed until 1 electron goes into 5d and 2 electrons go into that 6s. And so on down the list. This would be F3, F4, F5, F6. I'll just put that one in randomly just to give you an idea of what the patterns are. F7, F8, F9, F10, F11, F12, F13, F14. But those don't get organized until 1 electron goes into the 5d and the 2 electrons go into the 6s. Let's scroll down for just a second. This is what the periodic table of elements should actually look like. However, as a result of organizing it in this fashion, the boxes for each element are so small that the only information it can contain is an atomic number. And to chemists, they want more information about the elements in the periodic table. So to make life easier, this F block of elements is simply pulled out, and then the D block is smushed together so that we have what we would call our regular periodic table of the elements. And in this fashion, it fits on an 8.5 by 11 piece of paper with far greater ease. And as a result, our boxes are able to be larger in size so we can put more information in them. But truth be told, here's what the periodic table of the elements should look like. And this is the section that we're just talking about now. 6s1, 6s2, 5d1, and then that 58th electron, that's the first time you'll get into 4f1. But you don't organize that electron until you've got 1 in the 5d and the 2 in the 6s. And the same pattern exists as you look beneath. After 7s2, that box's pattern is going to say 6d1. That's technically not the valence shell. That's 7s2. This information gets translated down here. 7s2, 6d1. And then our first electron can go into the 5f1. But not until it's been placed in the 6d and the 2 electrons have been placed in the 7s. And so on down the row. Okay, here's where we were just focusing on. 7s1, 7s2, 6d1, 5f1, 5f2, 5f3, etc., etc., etc. So cool beans that our periodic table of the elements is really based upon the structure of the atom. How those electrons are arranged in the electron cloud is explaining why the periodic table of the elements is organized the way that it is. Let's take a quick trip back in history because it wasn't always like this. The first person who's given credit for organizing elements in the periodic table is a scientist by the name of Dmitri Mendeleev. Dmitry Mendeleev. He is given credit for organizing the first periodic table. And granted, he didn't have all of the elements that we have now, but he took the ones that he had in existence at the time and came up with a fashion for organizing them. He said that if we organize them by increasing atomic mass, that it would make sense and be predictable. So let's look at that. Hydrogen has a mass of 1. I'm rounding to whole numbers to make this go somewhat fast. Helium is 4. Yes, that's increasing. Lithium is 7. That's bigger than 4, increasing. Beryllium, 9, getting bigger. Boron, 11. Carbon, 12. 14, 16, 19, 20, 23, 24, 27, 28, 31, 32, 35, 40, 39. What? 39.9, that rounds to 40. 39.0, that's 39. Huh. That's out of order. Well, all right. I'll just count that as like one strike against us. 40, 45, 48, 51, 52, 55, 56, 59, 59. Oh, that really technically isn't an increase, so that'll just be strike 2. That's all right, no big deal. 64, 65, 70, 73, 75, 79, 80, 84, 85, all increasing. 88, 89, 91, so on and so on. 101, 103, 107, 108, 112. The numbers are getting bigger. 127, what? Oh, all right, another area where the numbers aren't getting bigger. Ugh. As a scientist, that's really annoying. Dmitry Mendeleev, why are the elements being organized by this when increasing atomic mass has things that are not in increasing atomic mass order? That's because Mendeleev said, I need to prioritize the groupings of similar properties within a family of elements. So he recognized that some of the elements went out of order if we focused on the atomic mass values. And he said, that's okay. I'm going to put them out of order because when I look at this family of elements, and that is what's called a group. And groups on the periodic table go in this column or up and down direction. That was the priority. Even though iodine has a lower mass than that of tellurium, I need iodine to be in this location because when I look at the other chemicals or elements in that family or group, they all have similar physical and chemical properties. And if I look at the other elements in the same family or group as tellurium, they have similar chemical and physical properties. So even though their atomic masses are going out of increasing atomic mass order, they've got to be put in this box, in these locations, because we're prioritizing the groupings of elements with similar properties. Well, that wasn't good enough to scientists. They understood and found that there was so much value in how Dmitry Mendeleev organized his periodic table, but they needed to find or come up with some explanation that doesn't have exceptions to the rule. And that comes back to what we were saying before about the structure of the atom. Here we showed how the electrons in the cloud can help explain the organization of the periodic table. But ultimately, the number of electrons in the cloud is really decided by the number of protons in the nucleus, or the atomic number. So Henry Moseley is the next scientist whose name we need to discuss. Where's my box? Here it is. Henry Moseley is the scientist who's given credit with coining or discovering the actual organization of elements on the periodic table. And he's the one who said, aha, if you do it by increasing number of protons in the nucleus, which is the atomic number, and remember, the number of protons is going to dictate the number of electrons in the cloud, there will not be any exceptions to those rules, and you will still hold true to Dmitry Mendeleev's grouping of the same elements with similar properties in the family. So no matter how hard you look at a periodic table of the elements, there will not be any exception to the elements being placed out of increasing atomic number order. Thank you so much for watching.